Okay, so like I said in the first few minutes, so until the pause here, I want to just do a presentation on video here where we discuss actually the deeper sides of electrodynamics. Okay, let's start with probably your first reflex. This is boring for many, many reasons. Okay, maybe you can already name me quite a few reasons here, but you've already kind of heard about it. You know that it's a theory which is essentially converged. Okay? When did it converge? It converged with the work of James Clerk Maxwell in the 1860s when he published his two books and essentially kind of nailed it. Okay? Maxwell's equations, everything that's needed to be known is there. The rest is just applications, engineering level stuff, nothing more to be discovered. Okay, that's an opinion. You've studied it before, and in the way that things are taught in many places, including here, you've had a few presentation flashes here and there. That's this, that's that, that's the Maxwell equations, that's how you use it, blah, 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 and then you're supposed to know about it. You know, it's like in the movies, you just get injected this theory, and then you're able to apply it. Of course, reality might not be quite so rosy. However, the fact that you've seen it before means that maybe, you don't really feel like it's very exciting. Maybe you're more practical. You say, hang on, quite frankly, if I look at the spectrum of available courses, I might prefer to have a course on, say, quantum electrodynamics instead of a classical one. I might really much rather talk about gluons and that sort of thing. Or really, if I want to be world famous, I want to talk about gravity. Okay, so why should I bother with electrodynamics? Well, that's a good question. Okay, and I'll try to convince you that there's still a lot in here. Okay, so there are many kind of fun historical anecdotes about electrodynamics, and one of the nice things is that these historical anecdotes are actually written up in various places. Okay, so it starts with some fun things with frogs. Yeah, so Galvani was kind of showing that indeed muscle movement had something to do with electricity. Then, the kind of morbid aspect of it carried on. The Italians at that time, they had, something in the water. I don't know. But even like plugged heads together and stuff like that. These things really happened. Okay? And more recently, actually, some other fun stuff has been done. So I'm not quite sure why, but frogs seem to suffer particularly from, electrodynamics. So these are experiments that were done on a Friday afternoon in Nijmegen. Essentially, you could use very strong magnets to levitate frogs. Okay, so you actually see a nice little video here of this frog studying essentially material polarization and things, and just induced charges and whatnot. This frog floating in space. Okay, so this famously led to an Ig Nobel Prize, actually, and then later the same person actually won the Nobel Prize of these things. But that was for the Ig Nobel Prize. Okay, so so fun little anecdotes like that for electrodynamics. But of course, you can get the morbid even better than that, and like Boris Christoph and things. These things were revived with electricity. So you think, if Dr. Frankenstein could do this and revive people from the dead, then surely as a teacher I should be able to motivate you with a bit of electricity as well. Okay, so we can talk about applications and stuff. Okay, so physicists in the 20th century, they came up with lots of good things for mankind. For example, thermonuclear weapons. And you can ask yourself, so you've heard essentially that the energy from these things comes from fission first and then maybe a fusion stage. In the case of fission, what happens clearly is that heavy nuclei get split, and then quantum chromodynamics determines what happens at the moment of splitting. But afterwards, really, what happens is an electromagnetic interaction between these two very highly positively charged ions. Okay, so the kinetic energy of the nuclei, what actually causes the explosion, is really electromagnetic in origin. Okay, so we call it a fission bomb, but really it's an electromagnetic bomb that is triggered by the fission moment. Okay, but the energy is really released through electromagnetism. So these nuclei, they fly out at about 3% the speed of light just from these electromagnetic interactions. Okay? When you think about classical electrodynamics, you really have to start from the very beginnings, kind of historical observations that were made pertaining to electricity. So what are these observations? First of all, for some strange reason, there are two sorts of electrical charge, like you already know. Okay? A much more surprising thing is that charge is quantized. Okay? It really seems to all degrees of accuracy that you always get total charges that are multiples of fundamental units. Okay? And this is not really properly understood. A nice thing is that charge is conserved, at least locally. So whatever happens when you sum up the charges, you always get the same value. And that really makes some of the calculations for the dynamics much simpler. And we'll see that later on in the chapter on conservation laws. A kind of not obvious thing is that the force has an inverse square form. Okay? We'll discuss that a little bit more in a few minutes. And I think maybe the most underappreciated fact of electromagnetic fields is that they obey linearity. So if you add the influence of multiple charges, it's just as if you have the charges in isolation, just put on top of each other. This is by no means obvious. Of course, it's a massive simplification for the mathematics of this, but it is really a not trivial fact. In fact, it's not quite true. Okay? In quantum electrodynamics, so, linear superposition really, because electromagnetism is transmitted by photons, linearity means that the photons are not interacting with each other. Okay? So in the classical electrodynamic theory, this is true. But in the quantum electrodynamic theory, this is not quite true. So you see this one, you have to put, a few marks on it because it's not quite true. For all practical purposes that you'll be confronted with, it is true, but it's not quite exact. But in this course, it'll be exact for us. Okay. Maybe some questions. So I want to start really from the beginning. You're already familiar with Coulomb's law and stuff like that. So, actually, by the way, one of the things I wanted to do with this course, in view of the current political situation, I think you have to be properly trained to detect bullshit and mark it and underline it. I think if we achieve something with education you're going to get at university here, is if we train you to essentially recognize falsehood and fight it, then we'll have achieved something positive. So in order to help you in this training, I was thinking that during each course, I would try to tell you one thing which is false. And then I'd like to know if you figure out which one it is. All right? So try to call off my bullshit. Okay? So maybe I'll try to do that. Okay? I'll try to do that, and then you can tell me what it is. Yeah? So just so you're a bit on your seat. Okay, so let's see. Let me ask you this questions. So first of all, you know the elementary charge, the electron and stuff. So, but did you ever ask yourself how accurately this thing is known? This is not a number like pi that you can just compute from basic principles. It's a fundamental constant of nature whose value is mysterious. Okay. I presume you've been introduced to the Millikan oil droplet experiment. Who knows Millikan's oil droplet experiment? Anybody? Yeah, you know. Okay, very good, very good. So what is this? This is quite straightforward in a sense, because what you do is that you build an electrostatic potential here between plates, and you literally vaporize tiny, tiny droplets of oil in which you inject charge, but as little charge as you can. And then what you try to do is to suspend the droplets in gravity and hold them with the potential that you put. And then you try to see, what the possible charge could be there, coming from, counteracting the force of gravity. So the nice thing here is that he was able to actually show that indeed the charge in these droplets seemed to be a small integer multiple of a fundamental unit, and this fundamental unit had a certain value, okay? So that's really not so long ago when you think about this, right? It's 100 years ago. 100 years ago, people had no clue what this thing was. In fact, many physicists back then, they even thought that atoms did not exist. This was a new thing. There was a fundamental paper of Einstein in 1905, okay? That is, I think, the most important paper of Einstein in 1905. And that's the paper in which he treats diffusion. And it's the paper in which, essentially, he demonstrates that through Brownian motion, we know that nature is made of atoms. So in 1909, this was brand new still. And many professional physicists, like I say, still did not believe in the theory of atoms. Question?
Wouldn't the proof of Brownian motion undergo the existence of water and molecules, not necessarily the atoms the molecules are composed of?
That you'd have fundamental units, yeah, is the important thing. That there's no continuum behind it. So the molecules would qualify as, if you want, discrete building blocks for matter. And then, you know, if you're able to break them into fundamental atoms, that's one little further step. But the idea that there exist some of these fundamental bricks that you build matter with, this was proven by essentially looking at Brownian motion. Like I said, this was the most important paper of 1905. Yeah? No hands going up? Okay, fine. Yeah. Okay. So for this, he got the Nobel in 1923. But, you know, when you think about it, this is not very precise, right? It can be much better. So do any of you have any idea what is the modern way of determining what the fundamental charge of the electron is? Or would you have a suggestion of how to do it? Huh? Okay, that's one way. How accurately could one do that? That would be... Yeah, it depends on the vacuum that you have. It would depend on the screening that you could do for the fields inside. Yeah? So that's one way of doing it. Yeah? In fact, historically, it was done that way. But actually, you'll be a bit surprised because there is an absolutely incredibly accurate way of determining the fundamental charge of a single electron. And that is actually to perform two experiments in solid-state physics with macroscopic samples. The first experiment is called the Josephson effect. What is this? You take two superconductors, you put a kind of insulating layer between them, you put a little bit of voltage difference between the two, and you observe the current that goes through this barrier. And this current actually oscillates with a frequency which depends exclusively on the ratio of these two fundamental constants, h bar over E. Okay? And because it's a very easy thing to measure current, to great accuracy, it's very easy to determine this ratio here. First experiment. Brian Josephson described this phenomenon when he was, I think, an undergrad student in Cambridge back then. Won the Nobel Prize just a few years after. The second experiment is the quantum Hall effect. You take a bulk sample of electrons confined to a two-dimensional layer, you put a magnetic field perpendicular, and you measure essentially the cross resistance as compared, you put like voltage difference, and you measure like the current on the other, in the other direction. Okay? It sounds extraordinary. It's a bulk sample. But if you look at the conductance of these things, this is a plot of the actual resistivity of these things, kind of same thing. What you get is that essentially the conductivity of this sample is an integer multiple of E squared over H. Okay? And once again, you can measure these things extremely accurately in the lab. And now it's great, you do these two measurements, you divide them one by the other, and you obtain the fundamental charge of a single electron to call it 10, 12 digits these days. Okay? And this is great because labs worldwide can easily perform these two experiments to locally calibrate their things to this result. Okay? Did you know about this? No? Maybe? Yeah, so these are the two statements here. Okay, so you see, the kind of reflex is that if we want to know the fundamental charge of a single electron, might as well do a measurement on a single electron. Okay, not so. The accuracy that you can get with this is way, way, way higher. Okay, and there are lots of magic tricks like that can be done. Okay. Then another question. So how accurately is charge quantized? So if I take electrons and protons, then how accurately is that known? Actually, there are a number of experiments that can be done. These days with cold atoms, you can really do modern experiments where you really check for the kind of neutrality of a compound of the two. So it's really known to, call it these days about 10 to the minus 30. Okay, so this is like rather accurate. Yeah, even if you take the wealthiest American and you divide his wealth by this, then you still get 0, which just tells you how small this is. Yeah? Okay, so so these are relatively modern tests. In fact, these tests are still ongoing. Okay, then another really, really fun discussion is about Coulomb's law. Okay, so Coulomb's law, the force between charges varies with, it's proportional to the independent charges, and it varies with the inverse of the square of the distance. Okay, but really, are you sure the exponent is 2? Did you ever wake up in the middle of the night thinking, I actually don't understand why this exponent is 2? And then you don't sleep anymore. Did that happen to you or no? So hopefully during this course, maybe tonight, yeah. So I would be very pleased if some of you woke up next night thinking, why the hell is this 2? Okay? So when you think about Coulomb's law, it looks utterly boring until you start asking questions. Why is it 2? And how accurately do we know that it is 2? Is it just that somebody told us? Or is it really a fact of nature? Is it something that we can't really measure very accurately, but it kind of simplifies calculations, therefore we do it like that? Okay? Yes?
Isn't it the power of 2 because the electric charge around a certain sphere is directly proportional to the charge inside it, and so it has to be, the surface of the sphere is directly proportional to r squared, therefore the Coulomb power is directly proportional to 1 of r squared?
That's a tautological reasoning, because you're essentially using a consequence of the 1 over r squared to convince me for the 1 over r squared. But I can very easily give you another potential which is different from 1 over r squared, for which the first statement is not true. Okay? So for example, you could have a different exponent for the Coulomb law, and actually maybe more related to quantum field theory and stuff, you could have a different spatial dependence for the potential. So here, force is 1 over r squared, potential is 1 over r. Okay? But if we imagine that the photon has a mass, okay? Photons are massless as far as you know. But let's imagine, for purpose's sake, if you're a theorist, you can just say, oh, here's the mass of the photon. So then instead of doing Maxwell's equations, you do other equations in quantum field theory. They're called the Broca equations. Okay? You can very easily give, theoretically, a mass to the photon. And then what happens is that there's a kind of extinguishing with distance of the potential, which is much faster than any algebraic power. Okay? So really, the limitation that we have on this power law can be translated into a limitation that we have on the mass of the photon. So can we put bounds on the mass of the photon? Okay, and that's a thing that's occupied physicists for quite a while, actually. I want to discuss a number of experiments here that you might not know about, starting from the very, very beginnings of electrodynamics. Okay. Do you know how one would go about measuring 1 over r squared, or 1 over r whatever? Have you ever looked at the experiments that did this? Or did you kind of, I mean, you seem to be like good theorists, right? Because we tell you 1 over r squared, and you seem to be like content with this. You don't say, why is this? You know, how do you measure this? How do you prove this? You know, what is this? And what if it was something different? What would that mean? Okay? So, you know, I'd like to stimulate those questions in you. Of course, you know this chap, no? Henry Cavendish. So what was his greatest characteristic? He would only speak to one person at a time. He was extremely shy. He died one of the very richest men in England at the time. Okay, so he was working in the late 18th century. And when he died, I think he was either the richest man in England or the second richest or something like that. Okay? And he spent his life doing experiments in physics, doing absolutely extraordinary work that he did not publish, and therefore it doesn't carry his name. So from this point onwards, I would like you to talk about Cavendish's law, not Coulomb's law, because Cavendish did the experiment in 1773, and Coulomb published his work in 1785. Okay? That's being a little bit unfair to Joseph Priestley, who actually suggested the 1 over r squared based on discussions with Benjamin Franklin. Okay? But Cavendish, I think, is the first one who really like properly nailed it. Okay? So, how did he do that? Well, essentially, he was going back to the principle that you referred to. If you have a 1 over r squared law, then there's some really important characteristic of it. That is, that if you have a spherically symmetric distribution of charge, then the field is indistinguishable from that of a point charge. And if you have a uniformly charged shell of spherical form, then the field inside the shell vanishes. Okay? So what did Cavendish do? Well, he rented a barn somewhere, and he built stuff, among which this one here. And this, it's really interesting, actually. You can find this on Open Archives now. James Clerk Maxwell, 100 years later, I think in 1891, more than 100 years later, went through the lab books of Cavendish and made a big commentary on them and published the whole lot. And that's why we know about these things. Okay? So what did Cavendish do? What he built is a contraption where you have 2 concentric shells of conducting material. And then in those days, they would manipulate electrical charge with these Leyden bottles. You've seen those in the museums. You just need to go to Haarlem and things, and you have those, like things you hold, like thermos things with the head of a duck coming out, and then you charge them, and you can touch stuff, and you charge it. Like huge, long-lasting condensers that you could use. So what the logic of Cavendish's experiment is as follows. He would put one shell concentrically inside another shell, and then he would make an electrical contact between the 2 shells with this little thing here, which was made of glass, an insulator, and then a little bit of metal so that he could make the contact between the 2. He would charge the outer shell, then remove the electrical contact between the 2, and then go measure the charge on the inside shell. And the way you'd measure charge in those days, this was the way here. See, these are like little threads that hold 2 metal balls. And if you touch a charged object with 2 metal balls that are conducting, then the charge will spread between the 2 balls and the balls will repel. So you can detect very small amounts of charge. So that's what he did. And Cavendish determined that the exponent for Coulomb's law, as it was not known back then, the exponent for what should have been Cavendish's law was 2 plus or minus about 1/50. Okay, so it's relatively accurate. But then Maxwell himself redid this experiment later, and he obtained, 2 more digits of accuracy to this by just being more careful. And actually, in the 70s, there was a famous experiment by these chaps here, who actually achieved rather remarkable accuracy to this, okay? By just essentially expanding on the idea of the Cavendish experiment, but now doing it with bigger shells and stuff that was actually time dependent. Okay, so you can look at the details of these experiments, but it's really meant to follow more or less the same principle. Okay, so you get some increasing accuracy on these things. Okay, but actually, so that's about testing the exponent. One can also test would-be photon mass on here. And here there are many, many different methods. Okay, so you can really do, for example, measurements of the velocity of light at different frequencies, see if that differs. You can actually do that with extraterrestrial sources. This is essentially much more accurate because then you're looking at stuff that has traveled, sometimes thousands of light years or even more that show you whether the light signals that are often correlated with each other arrive at the same time, being at different frequencies. If there was a mass to the dispersion, then you would have problems with that. Okay, so these laboratory tests of Coulomb's law, we've talked about it a little bit. One really, really nice one is an idea of Schrödinger in the 1940s. This was about essentially measuring the magnetic field around the Earth, around a planetary-sized object. And with accurate measurements of the magnetic field, you could determine whether the shape of the magnetic field had some strange features. And one of these strange features was like an extra field in the vertical direction that would ensue from the photon having mass. This same idea was used by space probes around Jupiter, and this remains the best extraterrestrial determination of the limit on the mass of the photon. Okay, all these things that you don't know that have to do with really classical electrodynamics. Okay, so these are things. So these are limits you can give with this. So with Heisenberg's uncertainty, you could say that the mass of the photon is bounded 10 to the minus 66 grams. So it's pretty small. But of course, if suddenly the photon had a mass, all hell would break loose. Yeah, everything would go wrong. Everything would go wrong with our models of cosmology and things like that, right? So energy balance in the universe would have to be revised, all these things. So we don't know, but we still know pretty accurately. Okay, some other fun questions you can ask. I'm sure, again, you will have woken up in the middle of the night, remembering what your teachers told you, that the electron is a point particle. And you say, what bullshit is that? That cannot be the case. It must be that there's a kind of finite size to the electron. That would be much more natural. The electron must be a little sphere. It's just we haven't resolved it, and that's it. Okay. Did you know that there's a fun consequence of that idea? I don't know if... yeah,
the electron consists of some sort of non-single unit, then the different parts of it, those are connected to the electromagnetic belt, so you can't have a single part that is more than a point.
Yeah, so how would you hold it together? Yeah, that would be a problem. So in a sense, then it becomes a little bit like the problem back then with nuclei. When Rutherford did his experiment, he showed that the positively charged part of the atom was concentrated in a fraction like 10 to the minus 4 of the size of the atom, and there was no known force able to hold charges to these small scales. And that's why essentially the nuclear forces came into play, because they could overcome electromagnetism at small distances. So we would need some other thing like that to explain this. But there's another really even more fun consequence.
We're talking about 1 over r squared, but what happens if r equals 0?
R is equal to 0, so that's a long-range force, right? No decay. So this would essentially not fit with any energy conservation law or whatever. You couldn't, if you went all the way to R0, you're really talking about infinite range interactions, and that would cause problems. So you would essentially have to forget about your idea of locality. Yeah, so anything anywhere could influence anything else anywhere else. So you can write mathematical theories that have these long-range interactions, but yeah, that's not the world we seem to live in. except in condensed matter, where I can give you examples of things with infinitely long-range interactions. But infinitely long range in a finite system with many, many particles. But then at some point it stops. But yeah, so that's a different direction. Okay, so, so like we said, there's a problem. The energy of the field diverges. Okay, but then, so if it's a point particle, but then if we give it a finite radius, it's good. The energy is finite. Okay, but the fun thing is that purely from electromagnetism, you now see that the electrons have a mass. That is, they have inertia. Okay, and the way this works is essentially you can model then the electron like a little shell, like this. And then the question is, what happens when you start accelerating this shell? And what happens is that because of the propagation of electromagnetism, because of Maxwell's equations, relativistic effects, if you try to accelerate an electron one way, it will like re-interact with its own electromagnetic field, and that will try to repel it. So that's like inertia. So people got really enthusiastic about this because they say, this is the origin of mass. Okay, it's just an electromagnetic effect on these structures. And this is really going back to very early people on this, but then also in the 70s, 60s, 70s, 20th century. Okay, of course, today we explain mass with the Higgs process and all these things, but back then this was kind of a cool idea, right? But it doesn't fit with what we know. But it's just too bad. It's a really, really cool idea. Okay? And what about then linear composition? Like I said, so maybe the true equations are nonlinear. Maybe these infinite energies would be resolved by a new theory that is nonlinear. Well, actually, you can really write down some of these theories. From the early days of quantum mechanics onwards, this was actually done. But these days, our knowledge has kind of converged onto quantum electrodynamics. And like I said, in that theory, there is a very, very tiny scattering of photons by photons, which is very, very difficult to measure. So the equations are actually not quite linear. Okay, so to summarize, I think I would really want you to realize that with classical electrodynamics, it's all very well, many textbooks have been written, but it doesn't mean that absolutely everything is completely understood. There are still things that can be worked out. There are still consequences of that might change one day, okay? And if you were to find a kind of failure of electrodynamics, that would really mean quite a lot of stuff, yeah? So you would forget about gauge invariance, you would get all these extra consequences. Okay, so just to give you some teaser of what might be fun with this, I was just giving you kind of a different way of thinking about these things. Okay? And I think it's high time for a break, and after the break, we will start with our beloved equations. Unless there are questions, or maybe you want to break first and then questions after the break. Okay.